Right. Thank you. Yeah, thank you all for having me here, giving me the chance to share some about what I've been working on. So we see children in the world can learn to walk, and then with experience, they learn to walk faster, more stably. And in robotics, you can program a robot to walk, but no matter how much this robot walks back and forth along the field, it's not going to get quicker or more stable. So in my research, I've shown how actually robots can learn from experience, and with experience, they can learn to become even faster and more stable when walking, in fact, faster than anyone had been able to program this particular robot before. The general picture of my research, though, is that I want computers and robots to be able to learn how to take actions to achieve goals. So not necessarily just focused on robotics, but potentially applicable to many more areas. What this means concretely is that the computer or robot, what I'll refer to as the agent, should be able to learn a policy which will map any given state of the world to an action to allow it to reach a goal. So this is the same as the goal of the field of reinforcement learning, and I think probably many of you all here are familiar with the many attention-grabbing success stories that reinforcement learning has been putting out that have come out of reinforcement learning the past few years. So superhuman performance at video games, superhuman performance at the game of Go, simulated robots learning to play soccer, and then also some industrial success stories such as web marketing. Some work done here at Microsoft has contributed to some of that, control of data centers, or control of home thermostat systems. But with all of these successes, if you look a bit closer, of course, what we can see is that these learning systems are not very efficient. This Atari video game result involved the agent taking 50 million actions before it had a good policy. In the game of Go, playing 21 straight days of self-play, millions and millions of games. And as one more example, these simulated robots here, a year and a half of compute time to learn all the skills to play soccer. So if we want this reinforcement learning to be applied to real-world robotics or healthcare or more data-scarce settings, there's still a lot of work to be done. And I think the question that many people in both industry and academia are asking is, can reinforcement learning be data efficient enough for real-world applications? So this is the question which has motivated my research as well. But I think before answering this question, there's actually another question that we should be asking, which is just how can an agent learn to predict the effects of its actions? Meaning, like, if I do this, then this is the outcome to expect, whereas if instead I did that, this is what I should expect. So I'm going to talk about a couple of different ways that we've looked at this prediction question in my research. The first one is just going to be given a fixed policy, a way of doing a task. What is the expected performance that we'll see when we run that, if we were to use that policy to accomplish the task? And the other thing I'm going to talk about is how an agent can predict how its actions will change the underlying state of the world. So I'm going to start with this question of how we evaluate the performance of just a fixed behavior. But before jumping into that, I'm going to briefly introduce the reinforcement learning setting. If you're already familiar with this, this is just like a way for me to kind of get some of my assumptions that I bring to the table out in the open, so we're all on the same page. So the reinforcement learning world has several components, how it's usually defined. I'm going to introduce these with an example that I'll use throughout the first part of the talk of an autonomous vehicle learning to drive to reach a destination. So the first thing you have to define is your state space. For the autonomous vehicle, this might be its position in the world or where other cars are relative to it. This is all the information that it needs to make decisions. The vehicle has available to it actions which influence the underlying state of the world, such as like steering the wheel, braking, or accelerating. And then there's a notion of reward which captures what it is to be successful at the task. So maybe it just gets a small reward for reaching its destination, and if it gets in an accident, it could receive a very large negative penalty. And then finally, the policy is what defines the behavior of the agent. So for any state in the world, the policy tells the agent how it should take an action to achieve its goal. Interaction in this setting happens sequentially. It's not just about choosing one action, but the agent will begin in one state. It will take an action receive a reward depending on how good that action was in the particular state. And then it will transition to a new state. And this process will repeat. And so one assumption I commonly make in my work is that this interaction will go on for some fixed number of steps, and then the agent can go back to its initial state and try the task again. And this whole sequence of interaction is referred to as a trajectory through state action reward space. Now, in reinforcement learning, the problem that most people think about is that of policy improvement. We're given some specific task. Let's find the policy which maximizes the amount of reward we can obtain. But there's another very important reinforcement learning problem, and that is just policy evaluation, where we are given a fixed policy. We're not going to try to improve it, but we just want to know how much reward should I expect to receive if I ran this policy. And I would argue that this is a more important problem than that of policy improvement. First of all, it's usually a necessary first step. If you want to learn a good policy, you should first be able to evaluate your current policy. And second, when you want to deploy systems in the real world, you really want to know how well is this going to do before I put it out there and have it interacting with real people and the real objects. So let me just go a bit more into depth on the policy evaluation problem. So imagine this autonomous vehicle has one of two outcomes it's going to see when it drives. And I'm definitely greatly simplifying here. Of course, in the real world, there's just an infinitely number of different possibilities that this vehicle could experience. But let's just say with very high probability, it reaches its destination, and with very low probability, there's a safety driver that has to intervene to prevent the car from crashing. And these outcomes we can quantify with the amount of reward that the vehicle would receive for them. So reaching the destination is maybe a small positive event. The safety driver having to intervene is a very strong negative event. So evaluating the policy is just a matter of evaluating the expected value of what the outcomes will be. But where this gets difficult in the reinforcement learning setting is that these outcomes aren't just kind of one-shot things, but they're actually they're happening in a trajectory. So we have a bunch of individual decisions which all kind of combine together to result in these outcomes. And so these probabilities are not themselves known. You can't just analytically compute what is going to happen when you run your policy. So one setting where this is really important to consider how we can do policy evaluation well. Actually, sorry, I'm getting ahead of myself. The more formal notion of this, instead of moving away from this example, is that we're given a target policy, which is what we want to evaluate. We're going to assume that the target policy is a distribution over actions given the current state. And what we want to know is what is the expected total reward that will be received along a trajectory when we run this policy. So why do we care about this? So imagine that you were an engineer at a self-driving car company. You had a new policy that you were considering pushing out to users that was going to be controlling their car. So one thing that I hope that a self-driving car engineer would do in this situation is before pushing that out, they would spend some time testing the policy, trying to get a very accurate evaluation of what is going to happen when we push this policy out to real users. And then after this testing phase, there would be a deployment phase where the policy would actually go out in the real world. And during the deployment phase, you could expect that there's going to be a lot less safety mechanisms that are in place if the policy does something really bad. So the testing time is where policy evaluation is very necessary. And so how I imagine this would probably be done is you would hire a very large number of test drivers. You'd give them a car running this policy. They would each go collect some trajectories running the policy and report back with how well the policy performed, quantifying this, of course, with the reward that was received. And from this information, if you did this, you could get an estimate of how well the policy was going to perform. So this is a very natural way to evaluate a policy, but what I would want to emphasize here is that it's a very passive approach to doing this. You're just running the policy and seeing what happens. And I'm going to talk in a second about why that's bad, but first I just want to say this. So the general way of doing this is what's known as Monte Carlo evaluation in a reinforcement learning setting, repeatedly run the target policy, observe state action reward trajectories, and then just average the total reward seen across each trajectory. It's a really simple way of doing this. The problem with doing it this way is that there may be very rare outcomes, but that they have a very large impact on what your estimate of your policy's value is going to be. So for instance, in this case, you're very rarely going to see the safety driver have to intervene, and so you may miss that, or you may, if you see it more frequently than it's true probability, you may get a very inaccurate estimate that way. So what this would look like is if this showing on the x-axis here how much data is collected, and the y-axis what your estimate would be, with the blue dashed line being the true value that you're trying to estimate. You might be overestimating your policy's value, and then when you get just like a single rare incident, your value is going to kind of swing around, and it's not going to be until you've collected a very large amount of data that just by the law of large numbers you would converge to getting a good estimate of your policy's value. So what would actually be better to do in this setting is to take a more active approach in how you collect data. In other words, what we would want to do here is we would want to increase the probability that the safety driver needs to intervene. And if we did that, we can get a better quantification of the impact of that event on our estimated reward. So if you're, I did say that policy evaluation is somewhat motivated by applications of safety. So I am now advocating that we should increase the probability of a very bad event. So if that sounds strange, it is exactly thinking about these kind of settings where we can possibly put safety mechanisms in place, like here a safety driver being there to intervene, so that we can just get a very good estimate of the policy's value before we're in a setting where there are no controls, and whatever happens is going to happen and maybe cause larger damages or something. So if you agree with me that being more active in how we do policy evaluation, increasing the probability of these significant negative events can be a good thing, there's still technical challenges which remain to be able to do this. So the first of these technical challenges is once we take a more active approach to data collection, we've shifted the distribution of the outcomes that we're going to see. And because we've shifted this distribution, we can no longer just average the rewards we observe like we do in the passive approach. And then the second thing is that because we're generating trajectories, you need a particular policy to be able to figure out how to generate these significant rare events. So we need to know what is the right data collection policy to be able to be more active. So it's in this second technical challenge where my work has made its contribution. I'm going to first talk a little bit about how we can address this shifting data distribution problem, as this is necessary for the second part. But before continuing, I would like to just to get some terminology straight. When I say the target policy, I mean the policy we wish to evaluate. And when I say the behavior policy, I mean the policy that we're going to deploy to collect data. So first, with this first issue, how do we handle a shifting data distribution when we change the policy we run? So imagine here that we're now running a behavior policy, which is with 50% probability reach the destination, and with the other 50% probability is going to cause the safety driver to need to intervene. So looking at just the first outcome, you can now see that we're going to be reaching the destination about half as often. So a very simple trick to correct for this is to just multiply the outcome you see by around a factor of 2. And so this is going to adjust for the fact that we're not seeing that event as much as we would have otherwise. The general way of doing this is a technique called importance sampling, and it's a widely used technique. I'm going to just briefly introduce it, how it's used in the RL setting. We first repeatedly run the behavior policy. We then add up all of the rewards received along each trajectory, just as we would in the passive approach. But then the key thing here is that we reweight the reward totals. And you don't need to understand exactly how this is done, but basically you're adding up the rewards as you would in the passive approach, and then multiplying by a relative likelihood factor. So this factor just says, if this outcome was more likely under my target policy than the behavior policy, increase the weight on it. If it was less likely, then let's decrease the weight on it. Once we've reweighted it, we can use our observed data as if it had come from our policy of interest. So this makes important sampling a very general technique. And it allows us to address the first technical challenge that we have here. But we still don't know what the right behavior policy is. And so that's what I'm going to talk about next. So myself and collaborators looking at this problem, we're asking the question of, what if we could only send out a single test driver in the setting that we've described? So we want to know, we have just, yes?
So kind of a conceptual question which is bothering me. So suppose I think about suppose there is a state where the safety driver needs to intervene, and I can think about roughly like reaching the state. So in terms of like think about a policy that gets me to that state half the time. In your example, for instance, I can have that goal in my mind, but then coming up with that policy seems roughly as hard as solving the reinforcement learning problem, because I'm thinking about now the ability to actually maximize this reward, which is getting to that state in the MDP. So I guess that's maybe the conceptual difficulty that I'm having, is that in order, like, is the problem of trying to figure out a good data collection policy going to be basically as hard as the reinforcement learning problem, or is there some structure that makes it easier?
Yeah, so that's a great question. First of all, I guess we're mainly focused on the problem of policy evaluation here. So I think the main question we're asking is just running that policy, using the target policy to generate data, is that more efficient than adapting your policy and using that to generate data? And so the answer, to skip ahead a bit in the talk, is yes, it is more efficient to do that. In terms of the policy improvement question, like could you adapt things we're doing here to that setting? The answer again is yes, in principle you could. There's some other challenges there as well. I guess also just intuitively what we are going to do is reinforcement learning for finding a better policy, data collection policy. So we started with this question of, what if we could just collect a single trajectory? Could we get a perfect evaluation of our policy with just sending out a single test driver here? So what this is again is the important sampling estimate. You don't need to follow all of the math, but we're basically saying with a single trajectory, this is what our estimate would be. And can we make this exactly equal to the true value of the policy? So it turned out that yes, you can do that. However, while it's like theoretically you can show it exists, you can't actually analytically compute what that best policy is. So we're going to do what Alec is suggesting here, and we're just going to we're going to learn what a better data collection policy is. So we write down an objective. This is done pretty standard in machine learning. You don't need to follow all of exactly what this is, but this is the mean squared error. So we basically look at the true value and our estimate of that value given some data, and we want to know like how far off are we from a squared error perspective. So you can't actually estimate this quality because it depends on knowing the true value of the policy, and if you knew that, you would already be done with the evaluation problem. However, what we showed in our work is that you can estimate the gradient of this objective with respect to the behavior policy. So this now gives us a mechanism for adapting the behavior policy towards one which will give us more accurate evaluation. What this looks like graphically is if you can imagine the space of all possible policies compressed along the x-axis here. We might start with the target policy, and if we use that to collect data, we could expect to have a certain amount of error on average. We then estimate our gradient, take a step along that gradient, and we end up at a behavior policy which on average will give us better data for policy evaluation. So if you're wondering how this kind of connects to the talk of increasing significant rare events, it turns out that the expression we derive for the gradient tells us exactly how to increase the probability of significant rare events that might be encountered. So again, you don't need to follow exactly what this expression says, but we have one factor which says for these actions, increase their probability, and another factor which captures the significant kind of how rare and significant the particular event is. And overall, this expression is saying if an outcome is like very rare and has a big impact, then increase the probability of seeing it. So we now have a mechanism that allows us to learn a better behavior policy. So what this looks like in this setting is we would collect a small amount of data using the initial target policy. Anytime we discover an event which is going to have a big impact on our estimate, we increase its probability, and this can be repeated until you have a very good data collection strategy. And really the key thing here is that you can always you can use all of the data you're collecting as you learn to also evaluate your policy. So there's no wastefulness here. This is is always going to improve over a just passive way of collecting data. The generalist strategy is that we're going to collect a small number of trajectories with the target policy, locally improve the behavior policy, and then collect more trajectories, and then we can use all of the data to evaluate it and optionally repeat this as many times as desired. And so with this contribution, we now know what the right behavior policy is, and we can use this for more accurate policy evaluation. So I'm going to briefly show some empirical results. These are on some reinforcement learning benchmark problems. The y-axis is mean squared error, so lower is better. And the x-axis is how much data has been collected. This is the Monte Carlo approach. It will get lower just because it's a consistent estimator of the true value. But if you're simultaneously adapting the behavior policy, you can get better more accuracy faster. And it's important to note that this is on a log-log scale. So these results are saying between 30 and 70% more accurate policy evaluation for any fixed amount of data that you could collect. So this wraps up the first part of the talk. Just the main takeaways from this is that first I would want to emphasize that policy evaluation is critical for safe and reliable deployment of autonomous systems. And that I think active data collection is a really important step to doing this reliably in practice. This work also connects to a larger question of counterfactual reasoning, which is very important for autonomous agents to have. And so my work has also made several contributions in these wider questions. One of our most recent results has again been looking at this important sampling type methods, which rely on computing a certain ratio. So we just presented some work showing that if you take the denominator of this expression, which is the true probability you were sampling data from, and replace it with its empirical estimate, that you can improve the quality of importance sampling. So that's some of the most recent work that we've done on this topic.
For the empirical results you showed 2 slides back, I guess I was kind of curious, in particular for the cart poll example, what would be, how should I think about the target policy? Is it a very good policy that's spending a lot of time in the near upright position, or is it a bad policy that's most of the time not getting there, because that's going to influence also the effect of policy adaptation, right? So could you comment on that a little bit?
Yeah, so in that case, that policy was partially optimized, so somewhere in between the two extremes. We have looked, so the amount of improvement you get is going to be dependent on how much variance is in the target policy return. So if you're running, it's one extreme. If you're running a target policy that always sees the same thing, there's no advantage to doing this. You're always going to see some improvement if there is variance in the target policy's outcomes. Yeah. So actually, I'm about to kind of switch gears and talk more about like a different part of the work that I've done. So if there's any questions on the first part of the talk, I could pause here and take a couple now. Yes.
So you showed results on like cardboard. What's the complexity? Like, what's the largest the state dimension that you actually experimented on? The cardboard is very small, right?
Yeah.
How does it scale? Is like basically the question.
Yeah. So I would say what we did, the basic method that we've implemented is essentially the reinforce algorithm. If you're familiar with this, for policy gradient methods. So we didn't take this beyond implementing this in like a kind of simple reinforce approach. In terms of, so we haven't really tried to scale it up beyond those much. But I would say, so reinforce was like a policy gradient method introduced in the early 90s. There's been a lot of literature showing how to scale that, and you could do a lot of those same techniques here. So, yeah. Yes?
Along the same question, like what was the horizon that you investigated in your problems?
So the ones I just showed, I think were both horizon of 200 time steps. Yeah, so, I mean, I guess, I don't know if like your question's kind of getting at some of like important sampling and long horizon issues. So I think it's, intuitively what's happening is that we're learning a policy which is going to be kind of close to the target policy, but if there's a way to get to these more extreme, like rare events, it's going to increase the probability of those actions. So you don't really have some of the same long horizon issues that would normally plague important sampling when your data is just given to you from some arbitrary behavior policy. In fact, here we're kind of using like the variance of the weights to counteract the variance of the returns there.
I mean,
so.
unless you find too much variance in your policy gradient as a result of the long run.
Yeah, no, that's so we didn't find it like too hard in practice, but yeah, like the one way this would is if you were trying to like use that gradient with a very poor estimate, then that would, yeah. Actually, but that answers the question. Okay, so now moving on to the second part of the talk. I also think it's very important that agents are able to predict how their actions influence the underlying state of the world, even in a somewhat task-agnostic way. So what I mean exactly by this, you can connect to model-based reinforcement learning. Again, going back to this autonomous vehicle example, we know that if this vehicle was to accelerate from standing still, that it would begin moving forward at a high velocity. But to an agent which is just beginning to explore what its controls do to change the state, this isn't at all obvious. So concretely, what I mean is that given any state and an action the agent may choose to take in it, we want to know what would be the predicted next state which is going to result, or possibly a distribution over next states. And I think this is really key to scaling up autonomy, because if we could do this perfectly, like the policy evaluation problem, we could do very data efficiently. Instead of like collecting any test trajectories, we would just simulate all the different outcomes, and we could know what any policy was going to do. Similarly, for policy improvement, instead of generating real experience, we could learn from synthetic or simulated experience in that way. So this part of the talk and the work we've done here is very much motivated by the gap we see in robotics between simulated and real-world domains. So in particular, this is a bit of experience that I have working in the RoboCup 3D simulation domain. So what is, I think, interesting to note here is just how smoothly the robots move. They're able to have these long kicks and move quickly to the ball. And the reason for this is that you can apply reinforcement learning in a domain like this. And you can heavily optimize all of the skills that the robots use, and so that you get something which is much, much better than you could possibly hope to hand tune. So let's contrast this instead to what we see on real robotics. So this is from the RoboCup Standard Platform League competition. This is a robotics platform that I've worked on throughout my time as a PhD student. And what you should notice here is that the robots are moving much slower. They're kicking the ball less far and less accurately. And there's no hope that you could really do reinforcement learning directly on this platform. the robots would break. Actually, I guess I saw that you all have a now robot on the 3rd floor. Like, just trying to imagine applying a reinforcement learning algorithm on it, you would need like a lot more robots. So one hope is that we can just apply the same learning that we're doing in simulation, and if we do it in simulation, then we can just put it on the physical robot, and it will all work out, and we won't need to actually do learning on the robot. So you can have this setting where you have an initial skill in simulation that maybe isn't working that well, like a slow walk. You can have the same situation on the physical robot where it can walk, but maybe not as fast as you would like. Apply a policy optimization algorithm in simulation, and what you get out is a much faster walk at the end. So then maybe you're done, you just take this faster walk, you put it on the physical robot, but unfortunately, what you typically see when you do that is that the policy finds something in the simulated environment, it overfits to it, and it tries to exploit that in simulation to get high reward, and that ends up failing in the physical world. So this is conjecture, but like what it seems to have happened in the video I just showed is that the robot learns in simulation. It can walk very quickly by just sliding its feet along the ground, and that doesn't work when you're trying to walk on carpet like this. So I'm going to show how we can actually learn in simulation and get it to transfer onto a physical robot and introduce an algorithm for doing that. Just to make this a bit more concrete, this is on the problem of a robot learning to walk. So in the general MDP setup for this, we have a state space, which is the position and velocity of all the robot's body parts. There may be other variables that we can't measure well. The action is the robot is going to choose commands for each of its joints, and we're going to reward it based on its forward velocity that it's moving. We just care about moving in a straight line. And so we want to learn a policy which tells us how to map the current positions of the joints to commands which are going to make it walk fast. And so you can think of this the trajectory interaction as happening in a loop where the agent is sending its state to the policy, and then the policy is responding with an action. So what we want to now do is replace, instead of interacting with the physical robot, we're going to interact with a simulated version of the robot and learn from the experience which is generated through this loop. There's a general methodology that we're going to build on in this part of the talk. This is known as grounded simulation learning. So what this is that we assume we have a policy we can execute in the real world. We can use this policy to generate an initial set of state action trajectories. These trajectories tell us what are the effects of our actions on the state of the world. It gives us some data that we can use to see what the effects of our actions are in the physical world. We then have a step of grounding the simulator, which means trying to make the simulator give us trajectories similar to what we observed in the physical world. Once the simulator is grounded, we then apply reinforcement learning on it, and we can now expect our improved policy to transfer back to the physical robot because we had this grounding step. So returning to this problem, I'm just going to make this a bit more concrete, and that what we want to do is we're going to receive the current joint positions of the robot, which can be obtained from its sensors, and then the policy is going to compute commands to send there. And so when we talk about grounding the simulation, what this means from the perspective of the policy is that somewhere between sending those joint commands to the simulation and getting the new joint positions back, we need to change something so that the resulting next joint positions it receives are similar to what it would had it taken the same commands in the real world. And so what we do in our work is we focus on modifying the joint commands that the robot sends to the simulation. And by doing this, we're going to change the commands in a way that makes the simulation give us back joint positions like what we would have seen in the physical world. Our approach to doing this is that we augment the simulation with what we call a grounding module. So when the robot sends its joint commands, they first get passed through a grounding module, which is going to transform them and then into a modified joint command, which is going to cause the simulation to respond differently than it would have had we just passed in the original commands. And we can construct this grounding module through two supervised learning problems. So the first step of this is that we're going to observe our data, and we're going to learn how to predict what the real-world effect would be based on the data that we've observed. So this is a supervised learning problem in that we have real-world data, and you can chop up this trajectory and get a set of state, action, resulting next state, at least for some components of the state features. And so now we can just train a model which tells us what is going to be the real-world effect given some actions. We then need to just choose an action which is going to cause the same effect within the simulated environment. This, again, can be done with supervised learning. We can collect state action trajectories in simulation and learn an inverse model, which tells us for any transition what action will cause it, basically how to reproduce the same effect in the simulated environment. So once we have this grounding module, we just incorporate this into the reinforcement learning loop here. And from the perspective of the policy, it's going to look as if it was interacting with an environment more similar to the real world. So I'm going to discuss or show you one application of this to the task of robot walking. This is, again, learning on the Now robot that we use in the RoboCup competitions. We're going to do 5 minutes of walking on this robot to collect the real-world experience. And then we're going to apply a reinforcement learning algorithm in simulation, which requires 5,000 minutes of walking. This would be a completely intractable amount of experience to collect on the physical robot. So this is the initial walk that we start with. One important thing to note here is that this is a walk engine which was developed for the RoboCup competitions. So there's a lot of people throughout the world trying to make this robot walk very fast. And this is, as far as we know, one of the fastest walks that people had developed for this robot. So then we can put the same walk directly in simulation. This is it just kind of moving normally along before we've done any grounding. We then apply the grounding algorithm that I just suggested. And you're going to see that the robot is going to begin having a bit more trouble to walk. It's going to become a bit more unstable. So this is more like what we see when the robot is walking in the physical world than when it's walking in the simulation environment. So once we then apply reinforcement learning in the grounded simulation, just doing kind of local policy improvement on the policy, we end up with a walk which is 40% faster than the previous walk we started with. So this is now. And as far as we know, this is as fast as anyone has gotten this robot to go. So to conclude this part of the talk, I again just want to emphasize, I do think that better action modeling is like a very important step towards long-term autonomous agents. They're going to be able to do a lot of things in the physical world. And that in a lot of real-world problems, not just robotics, although certainly robotics is a great example, there are existing domain simulations, and that when these simulations are available, if we can leverage them, then it's going to go a long way towards efficient reinforcement learning. There are, of course, also environments where we don't have good domain modeling, and I think being able to model a domain from scratch will also be an important capability for autonomous agents. We've also done some other work relating to how you can use domain simulations to try to put confidence intervals around the performance of policies when you're interested in things such as safety of deploying a policy. So this wraps up the part of the talk. Just there, I wanted to introduce some of the work that I've done throughout my PhD. Before concluding, I'm just going to talk a little bit about some of the next directions that I'm really interested in exploring towards making reinforcement learning data efficient enough for the real world. As just a general comment before getting into the specific research directions, I think that studying reinforcement learning both from a more theoretical side or a more algorithmic side, as well as trying to apply RL to problems where it just falls flat on its face at the current moment, is a really important way of doing research. So one of the problems that I plan on continuing working on long term is this problem of robot soccer. It would be just really intractable right now to imagine learning this task from scratch. And so I think this is a really good test bed for RL algorithms. I think it's also really important to work on multiple application domains, as you don't want to necessarily produce, at least for me, it's important to not just produce algorithms which are only specific to one test area. So throughout my PhD, I've also been doing work on traffic systems for autonomous vehicles, not necessarily just learning, although we are also looking at reinforcement learning in this context. And moving forward, I'm hoping that just by working across different application areas, there's the potential to develop algorithms which are applicable to many different areas. So in terms of the research directions, which I think are really promising to explore for achieving this, I think looking at things such as state and action abstractions is important for scaling RL. Understanding the theoretical properties of methods that we propose are important for having reliable methods that we can trust in practice. And finally, although I focus on prediction, I think that there's still going to be some steps left from connecting prediction to better policy improvement. In terms of state and action abstraction, the basic idea here is you can think of that an agent has different levels at which it can make decisions. So for an autonomous vehicle, maybe it has an action drive home, which itself is constituted by the different directional turns that it has to make along the way. And each of those is made up of even very lower level controls beneath the hood there. So in RL, reasoning at the right level of temporal abstraction is really is a big impact on how effective your algorithm can be. If you're trying to do, if you imagine trying to get a vehicle to learn to drive home, and it's reasoning about this very low level of actions, it's a very difficult task compared to trying to reason at a higher level of abstraction. One problem that I'm particularly interested in this space is the ability to learn in very low fidelity simulations. So if you can imagine in the game of soccer, you could be simulating at the level of the robot's the control of each of its individual joint motors. You could also imagine simulating at the level of just circles passing a ball around. One of these problems should be significantly easier to learn in, not necessarily easy, but easier to learn in for things such as strategy. And so, what is the right level of trade-off? What can you learn in a very abstract representation that then and can then be transferred back into the real task of interest? I also think with introducing abstraction, you're introducing approximation, which can hurt the guarantees that you can put on methods. I think it's really important that we establish the properties of methods that we're developing. So, for instance, statistical properties, such as just what is the confidence that I can have in my estimator, or is a method consistent, meaning do I eventually get the right answer with just enough data? So I think being able to establish methods like this are very important for practitioners to be able to trust what we do. Similarly, it's also important to be able to show that your methods are scalable in the sense that if a practitioner can't use it, it doesn't really matter how good the guarantees are. And also explainable so that you know why your predictions are what they are. So finally, most of what I do focuses on prediction, but I think there's still, even once we can do perfect prediction in the space of modeling the effects of actions or evaluating a fixed policy, there's still going to be some questions open to connect this to efficient policy improvement. So I'm very interested in looking at how do we search the space of all possible policies to find the best one for a task, or once we learn on one task, how can we transfer what we learn to a new task? And so I think once we can do kind of all of this, we're finally going to be able to answer the big question and say that reinforcement learning can be data efficient enough for real-world applications. And so that's what I'm looking forward to continuing on to do. Just before wrapping up really quick, of course, there's a lot of people who've contributed to this research. My advisor, Peter Stone, has been involved with all of this. The first part of the talk was done in collaboration with Scott Neekum at UT Austin and Phil Thomas at UMass Amherst. And then the work I've done in the space of traffic systems for autonomous vehicles that I unfortunately couldn't spend time on today has had a very wide number of collaborators as well. So with that, thank you all for coming to the talk today and giving me your attention. And I'd now be happy to take more questions. Yeah.
So the second part of your talk, it reminded me a lot of like iterative learning control, right? And so if you know, familiar with that, right? Like where you basically memorize what the deltas are, and you keep on iterating until you come up with a policy that acts in the real world like you would expect it to.
Yeah.
And usually control people started doing that because they found that for complicated any system, modeling is just hard, right? So they're like, so iterative learning control is nothing but fancy words for I'm going to bypass modeling and just learn a nominal model and I'm going to learn the deltas. Now there's this like, one way is you learn an explicit model and find the deltas in the model, the residuals in the model that matter in the spaces that you care about. The other way is I'm going to just completely bypass modeling and learn a good policy, right? Yeah. And it's, unless I missed some details, it seems you are taking the route of like, I'm going to bypass models, right?
Yeah, well, kind of both, in that we're leveraging a simulation, which itself is a model of the world, and so, but within that simulation, we are learning in a model-free way, where we are just trying to directly get a good policy there. Yeah. Right.
So, would you comment on what your thoughts are? Like, is there any advantage to see in that specific domain? Let's say with the now, those are super hard to model, by the way, and can we do approximate models and then learn, inject that habit in the simulator, and then learn the deltas that you would need to learn?
Yeah, no, I think that's a really good question. So I think what we're doing is actually somewhat similar to that, in that we are inherently kind of locally modifying the simulation. So back a few slides, was kind of showing this process as a loop. That's because like when you try to modify the simulation in a I guess a data-dependent way, it's going to be inherently bound to what that current distribution of data you get from your policy is.
Exactly.
And so in that sense, we're correcting the policy. We're correcting the simulation local to that particular policy, optimizing there. But then we have to go back to the real world and get more data to continue that process. So it's it still has this like same, at least like high level, like iterative learning approach.
I have follow on this other.
Maybe folks who are not.
Yeah.
So I'm curious to what extent you can correct the simulation just by changing the action space. Like often a lot of the errors in the simulation could come from the physics that it's simulating. Like you said, the carpet, is much rougher in real life, and just lifting your foot higher doesn't necessarily cover that in all situations.
Yeah, that's a good question. I guess so part of it is that we've done this. I was talking to someone about walking. We've looked at some other tasks with the Now robot and found that we can correct things. I could imagine situations where correcting the actions isn't sufficient to do it. But it does. So in like some, even in like, we're not necessarily, so with the carpet and stuff, you can even though that is like a physics parameter that could potentially be adjusted as well, you can actually like kind of see things getting captured in like how it changes its motions. Like if the foot is getting stuck on the carpet, then in simulation, like instead of like letting your foot move as freely as it would, then by changing the actions, you can make it appear as if it was getting stuck more on the carpet. So I think like you can like kind of capture some of these things by just modifying the actions as well. I think there's definitely some things that it wouldn't be sufficient to do as well, though. So.
Going off of that question as well, the kinematics of the actual little robot, these robots are notoriously bad at having like correct joint positions, right? So how much, I guess, did you run experiments to see how much better your algorithm gives this kind of like transfer to real life versus just injecting random noise to the motors? Because if you were to take random permutations of the motors, like how much better does your simulator approximate that instead of just like tweaking all of your little motors continuously to try and inject that kind of real world problem into the agent?
No, that's a good question. So we did look at that baseline as an approach, and so I can what we did gave it ended up with like faster walking performance. I think the other interesting like kind of trade-off you see with those methods is that like by like injecting noise, you can learn more robust policies. So I guess going back to the notion of local improvement of the policy, if you inject noise, like we could learn for longer, and you could still get like some stable policies that would transfer to the robot, but then you kind of gave up some of the like exploiting the real world. So like not as fast, but still stable, if that makes sense.
Yeah, but I mean, at the same time, like, your algorithm that tries to approximate the real world might have some error that then you're still translating error to the robot.
Yeah, exactly. There's still error. I guess what we saw, like, kind of empirically, was that I guess less error than just kind of adding noise into things.
But it's cool to see the result of. So is that like truly the documented fastest walk for that little guy?
So we took. This is like, I guess it's mainly based on, so the RoboCup competitions are like. There's like a lot of people trying to get the fastest walk on these nows. We used this in the competition last year, and there weren't teams using a faster walk than this. As far as we know, like reported speeds, it is as well. So
I feel like there needs to be like a subtask in the nano competition of like who can make the nano walk fastest, because I've seen a lot of work with that.
Yeah, so there is some. There's some work on like trying to get them to go just like incredibly fast, and you don't care if the robot falls over at all. So in that case, that's not exactly what we're trying to compare with here, because we want to get something which is actually useful for like the task of RoboCup. So this is like both fast and stable, whereas you can get them to go faster if you're willing to have your robot fall over like at the end of its run or so. But yeah. Yeah.
All right. Well, let's thank Josiah again.
Yeah. Thank you all.